times the sine of theta, 30 degrees, which equals 6 meters squared per second squared.
To figure out which direction the product vector is going, like if it's going out in a positive or negative direction, all you need is your right hand.
What you do is place the extended fingers of your right hand in the direction of the first vector, and then bend them so that they point in the direction of the second vector. So you're moving your fingers from the direction of vector A to the direction of vector B.
If you find yourself trying to bend your fingers backward, just turn your hand over so your fingers move easily into the second vector. Now extend your thumb. The direction your thumb is pointing is the direction of the product vector. The product vector will always be perpendicular to both vector A and vector B.
So, in our example, the direction of the product vector is going down through the page, perpendicular to both vectors A and B.
It's easier to visualize which way the product vector is going if we diagram the vectors on a piece of paper, like this one here. So, from our problem, we have vector A with a velocity of 3 meters per second and going at an angle of 60 degrees. Vector B's velocity is 4 meters per second with an angle of 30 degrees. Now, let's put the paper in front of us, keeping in mind that the product vector will always be perpendicular to the two vectors we started out with. Extend, cross, stick out thumb, and voila! The thumb is going through the paper!
Another way to multiply vectors is by cross-multiplying. Do you remember this, the table for cross-multiplication?
Well, actually, to cross-multiply, we must first have the components of our two vectors. Then we can set up the table for cross-multiplication. We put the components of vector A sub x, and A sub y in the first row. In the second row, we put the components of B sub x, and B sub y. And voila, the table for cross-multiplication.
Using this table, we multiply diagonally down from left to right and subtract the product multiplying diagonally down from right to left. So the cross product equals A sub x times B sub y minus A sub y times B sub x.
Using the components in the roly-poly example, we've got 1.5 meters per second times 2.0 meters per second minus the product of 2.6 meters per second and 3.5 meters per second. That's 3.0 meters squared per second squared minus 9.1 meters squared per second squared, which is negative 6.1 meters squared per second squared.
When we cross-multiply vectors and get a negative product, it means the direction is down, into the paper. If the product has a positive value, the direction is up, out of the paper.
After all that, to find the direction of a vector, remember that right-hand rule. Diagram on your paper the magnitudes and directional angles of vectors A and B. Extend and cross. Stick out your thumb, and you've got the direction of the product vector. If it has a negative value, the product vector is down, into the paper.
There are two ways to multiply vectors. We can either use the dot product, which gives us only magnitude, or the cross product, which gives us magnitude and direction. Product A dot B equals the magnitude of A times the magnitude of B times the cosine of theta. Or, using components only, the dot product equals A sub x times B sub x plus A sub y times B sub y.
For the cross product, we use the formula the magnitude of A times the magnitude of B times the sine of theta, which gives us the magnitude. We use the right-hand rule to get the direction. If we only have components, use cross multiplication. A sub x times B sub y minus A sub y times B sub x. The right-hand rule is used to find the direction of product vector. Remember, extend, bend, and stick out the thumb.
Coming up is one-dimensional kinematics. One-dimensional, like the woman who tore out my heart and kicked it to the curb. Yow!
Part 3, One-Dimensional Kinematics.
One-dimensional kinematics focuses on motion along a straight line.
The three basic quantities of one-dimensional kinematics are displacement, velocity, and acceleration. Now let's look at each quantity one at a time.
Section A, Basic One-Dimensional Quantities.
First, displacement, or delta x as we represent it symbolically, is the change in position of an object. The standard unit for displacement is the meter. We can find an object's displacement by subtracting the object's initial position from its final position. So, displacement, delta x, equals x final minus x initial. Here's an example.
Say Not Quite Bright, the one-dimensional Wonder Boy, starts from the ski lodge at a position of 2 meters and stumbles over to put on his skis at a position of 5 meters. The displacement of Not Quite Bright is his final position, 5 meters, minus his initial position, 2 meters. 3 meters. No sweat, right?
Next, average velocity, represented by a v with a line on top of it, is the change in position, or displacement, delta x, of an object relative to the change in time, delta t. We just saw how to get displacement. Delta x equals x final minus x initial, where the unit of change in position is the meter. The change in time, delta t, is like the change in position, where delta t equals final time minus initial time, and the unit for the change in time is the second. So the average velocity equals delta x, the change in position, over delta t, the change in time. And the unit of average velocity is meters per second.
An example of average velocity is miles per hour, like when you're driving a car or riding a bike. For example, Not Quite Bright may tell you that he was skiing 40 meters per second down the mountain, which is about 90 miles per hour. Children, can you say faceplant?
So Not Quite Bright's cruising down the slope at 40 meters per second. But that doesn't mean that he's been skiing 40 meters per second the whole time. That number is just his average velocity. Not Quite Bright could have been at 20 meters at 2 seconds, then at 100 meters at 4 seconds. But what is his average velocity? His average velocity between these 2 points equals the change in distance, delta x, over the change in time, delta t. So put x final minus x initial over t final minus t initial.
That's 100 meters minus 20 meters over 4 seconds minus 2 seconds, which equals 80 meters divided by 2 seconds, or 40 meters per second.
Now you can see how 40 meters per second is really an average velocity, since our skier may have sped up or slowed down between endpoints.
Now let's average acceleration. Average acceleration, represented by an A with a line on top, is the change in velocity, delta v, over the change in time, delta t. The unit for average acceleration is meters per second, or meters per second squared.
Like we just saw with average velocity, the average acceleration is the average of more than one rate of acceleration.
Now that we've learned about the average velocity and average acceleration of an object, it's time to learn about the instantaneous velocity and instantaneous acceleration of an object.
The instantaneous velocity is simply the velocity of an object at a given instant in time. Same thing with instantaneous acceleration. It's the acceleration of an object at a given instant in time.
One last point about velocity and acceleration.
Note that any time we end up with a positive velocity, that means that the object is going in the positive x-axis direction. So, if we end up with a negative velocity, that doesn't mean that the object has imploded. It just means that it's moving in the opposite direction.
We can label any direction we wish to be the positive direction, so long as we never change it. Like if you're going to class, that's a positive direction. If you get halfway there and realize you forgot your homework and turn around to go get it, well, that's a negative direction. The easiest way to think about this is just to label the direction in which an object first moves as the positive x-axis direction. A negative velocity means that the object is moving in the negative x-axis direction. So, the negative direction is just opposite to our positive direction.
Now let's talk about acceleration. If you end up with a positive acceleration, that means that the object's velocity is increasing or speeding up. And a negative acceleration or deceleration means that the object's velocity is decreasing or slowing down.
Now it's equation time.
Section B, one-dimensional kinematic equations.
We're going to give you 3 kinematic equations that you'll use all the time. So learn them, love them, become one with them.
These are the equations. There they are. Yep, that's them. There are 2 conditions necessary to use these equations. First, the object must be traveling in a straight line. And second, the object must have a constant acceleration. That is, the average acceleration has the same value all the time.
The first equation we use to obtain